everyone. In this video, we are going to continue interpreting graphs. And we're going to start with this graph, which represents the function f. And the first two problems are really review. Remember, in the last video, part 1, you learned how to evaluate a function graphically. And that's what we're doing for example 1 and 2. So just a little bit of review. So remember, if you want to find f of -5, if we want to figure out what that equals, then this is saying to find the y coordinate when the x coordinate is -5. Okay, so I would go to -5 on my x-axis, go up to the graph, and we're just trying to figure out what that y value is for this point. Remember, writing function notation is no different than writing an ordered pair. Okay, just different ways to represent the same thing. And again, we would just be identifying this point that is on the graph of f. Okay, if we want to find f of 1, here's 1 on the x-axis. So again, I'll go up to the graph, over to y, and my y coordinate for that point would be 4. And again, we're just really identifying this point right here. It has the ordered pair 1, 4, so when x equals 1, y equals 4. Okay, now getting into some new stuff. How do we find the domain and the range of a function graphically? Well, remember that domain stands for the x values, or the input, or the independent variable. So graphically, when we're finding domain, you want to look at the graph from left to right, okay? And we're just explaining what the x values are for that particular graph. So I'm noticing, if I read this graph along the x-axis, that the x values start at -6 and then stop at +8. Excuse me, stop at 9. And I'm using brackets because there are closed circles at the end of the graph. There's a closed circle on the left end and a closed circle on the right end. Just to throw in some different possibilities. Let's say for this graph that this had been an open circle instead of a closed circle. Then when I find the domain, I would use parentheses on the -6, comma, 9, and still a bracket on the 9 because of the closed circle. Okay, so it is important that you get the parentheses and the bracket correct when you're finding domain and range, because remember, there's meaning behind the notation. When we use parentheses, we're not including that number in the interval, and when we use a bracket, we are including that number in the interval, okay? All right, to find the range, remember, range stands for y, or the output, or the dependent variable. So when you're finding the range graphically, you want to read the graph from the bottom to the top. Okay, so if I look at this graph from a different perspective, like here's the bottom, here's the top. And you're reading along the y-axis now, so that's why we're reading it from the bottom to the top, okay? So again, we can represent the range using interval notation, and you might notice that our y values start at 0 and stop at +9. And again, I'm using a bracket because of the closed circles at the end of the graph. But if there had been an open circle, I would have used parentheses. And anytime you have an arrow at the end of the graph, then you would want to use positive or negative infinity in your interval. Okay, let's look at one more example. So this time we're looking at the graph of g, the function g. And again, just back to evaluating, if we were finding g of 1, let's see, here's 1 on the x-axis. If I go up to the graph, it looks like y would equal 2. To find g of 5, here's 5 on the x-axis. Go up to the graph, over to y, and it looks like the y coordinate equals 6. All right, domain and range. Okay, so remember, to find the domain, you want to look at the graph from left to right. And, you are scanning that graph. So I can see that my x values start at -7. And again, I'm using a bracket because of a closed circle. And then if I scan my graph, okay, this part of the graph is kind of interesting. There is a break in the graph, but there really is no break in our x values because even though we have an open circle, we have a closed circle right above it, okay? So there really is no break in our x values. So I could actually just keep going from -7, and it looks like my x values stop at +8. And again, I'm using a bracket because of the closed circle. Okay, to find the range, again, we're just going to change the perspective. We're going to look at the graph from the bottom to the top. And again, as I'm scanning over this graph from the bottom to the top, I know we have a break here, but we really don't have a break in our y values because we have part of the graph right here. So our y values stop at +6. So our range would be, it looks like our y values start at -3 and then continue to +6. And again, I'm using brackets because of the closed circles. Okay, so to find domain, just read the graph from left to right. And to find range, just read the graph from bottom to top. And just be careful. It is important that you get the parentheses and brackets right when you're finding domain and range. Okay, now, another way that we might interpret a graph of a function is to find intervals where a function is increasing and where a function is decreasing. So a function is increasing on an interval if its graph rises as you move from left to right over the interval. Again, another way you can think of this, since we read the graph from left to right, x is always increasing, so we're saying as x increases, y also increases. Okay, a function is decreasing on an interval if its graph falls as you move from left to right over the interval. So again, what we're saying is, as x increases, y decreases. All right, and then a function is constant on an interval if its graph is a horizontal line over the interval. All right, let's look at some examples. So here are some examples. The first graph represents an increasing function. The second graph represents a decreasing function. And then the third graph represents a constant function. Okay. Now, it is possible that you have the graph of a function that might increase, decrease, and is constant on different intervals. Okay, so here is an example of that. So let's say we want to find the intervals where this function is increasing, decreasing, and constant. Okay, now here's the thing. We read the graph from left to right along the x-axis, okay? So when you're writing intervals of increase, decrease, and where the function is constant, you want to use x values, not y values, okay? So for instance, and I always kind of just like to start at the left and, you know, read it from left to right. So I'm noticing that first the graph is a horizontal line, which tells me that the function is constant. And it's constant until we get to this point right here. But sometimes I'll put these little dashed lines because we're reading it along the x-axis. So we would say that this function is constant from negative infinity to -4. Okay? Negative infinity to -4. All right, then the graph starts to increase. So the graph is increasing until we get to this point right here. So if I do this little dashed line, the dashed line just helps me find that x value. 1, 2, 3, 4. So we would say that this function is increasing from -4 to +4. Okay, and then the graph of the function is decreasing, and so we can say that it's decreasing from 4 to infinity. Okay, so you guys, a common mistake that students make, and it's really easy to do because like you're reading the graph and you're thinking, oh, the graph is increasing, it's going up, the graph is decreasing, it's going down. So it makes you focus on the y values, but when you write your intervals, you're using x values. Okay, so you know, you try this trick that I showed you with the dashed lines, because now you can see how we took that coordinate plane and we split it into 3 intervals along the x-axis. Okay. All right, the other thing I want to emphasize, or you may have noticed, is that I use parentheses with all of these intervals. So the reason that I did that is because at the point, like for instance, at this point and this point, that is where a change is happening. Like the graph is changing from being constant to increasing, or the graph is changing from increasing to decreasing. So we're not going to include those points in the intervals, and so that is why I am using parentheses instead of brackets on intervals of increase, decrease, and where the function is constant. Okay, moving on. All right, another way that we might describe a graph of a function is to identify what we call extrema, or extreme values of the function. And I mean, if you think of the word extreme, you know, we're talking about basically the high points and the low points on the graph of the function, the peaks and the valleys. But there are some different types of extrema, okay? So the first type is called local extrema. So you could have a local maximum or a local minimum. Now, sometimes instead of the word local, we will use the word relative. They mean the same thing. Relative extrema, local extrema are the same thing. In this case, we are just identifying the high points and the low points throughout the entire graph. Okay? So it's possible that a function can have several local extrema, okay? All right, now, how do we tell if it's a maximum or a minimum? Well, a function f has a local maximum, and the plural form is maxima, at x equals c, if the graph of f has a peak at the point c comma f of c. Okay, so this means that if f is increasing on an interval, left of x equals c and then decreasing on the interval right of x equals c, then f of c is a local maximum, okay? So all we're saying is if you have a graph that changes from increasing to decreasing, then we can identify that point as a local maximum. All right, a function f has a local minimum, and again, the plural form of the word is just minima, at x equals c if the graph of f has a valley at the point c, f of c. So this means that if f is decreasing on an interval left of x equals c and then increasing on the interval right of x equals c, then f of c is a local minimum. So again, all we're saying is if you're reading a graph and the graph changes from decreasing to increasing, then that would identify the point where that change happens could be identified as a local minimum. Okay, and then remember that a function can have several local or relative minima and maxima. All right, here's a visual for you, and I think this might help you understand. So let's say this is the graph of our function, and you can see like this graph is increasing and then decreasing. So that would make this point a local maximum. And then we see a change. The graph changes from decreasing to increasing, which would make this point a local minimum. Okay, then we have another change happening. The graph is increasing, then decreasing, which makes this point a local maximum. And then the graph is changing from decreasing to increasing, which makes this point a local minimum. Again, you're just identifying the high points and the low points as you read the graph from left to right. Okay, so let's practice this a little bit. So let's say this is the graph of our function, and we want to identify the local or relative extrema, and then also the intervals of increase and decrease. Now, personally, I like to start with the relative extrema because those are the points where the graph changes from increasing to decreasing, or vice versa. And it's pretty easy to identify your relative extrema. Again, you're just looking for a high point or a low point as you read the graph from left to right. Okay, now how can we identify these? There are many different ways you can identify these points. Well, first of all, let me just say that this would be a local maximum, and this would be our local minimum. You are identifying points, so you could always use an ordered pair. So the ordered pair of our local maximum is -3, 4. Instead of writing an ordered pair, you could use function notation, and we could say f of -3 equals 4. Or we might even write this out in words where we would say, okay, let's say this is f of x. Our function is f of x. We might say f of x has a relative, or you could say local, maximum value of 4. Okay, the value is always the y-coordinate at x equals -3. Okay, so if we're finding a maximum or minimum value, we're always finding the y-coordinate. The x-coordinate just kind of tells us where that is happening on the graph, okay? And you can kind of see where those words, using words like that, might fit better in a real-world scenario. So think about the turtle crossing activity that we did. In one of the problems, I think we found that the turtle had traveled like 8 feet. And so let's say that was the maximum distance. We might say the maximum distance of the turtle is 8 feet, at 2 seconds. Okay. All right. Local minimum, again, we could represent this point 3 different ways. We could represent it with an ordered pair, and so it looks like our ordered pair would be 3, -4. We could use function notation and say f of 3 equals -4. Or we could write it out in words and we could say f of x has a relative minimum value of -4 at x equals 3. All right, and then your intervals of increase and decrease are pretty easy because once you have identified your relative extrema, remember those are the points where the function is changing from increasing to decreasing or vice versa. And so now we can just identify those intervals, but remember you're reading the graph from left to right, okay? So again, a trick is to put those dashed lines through your relative extrema and then just read the graph from left to right along the x-axis. So, you know, we're starting at -infinity, and I can tell that this graph is increasing until we get to -3. So this graph is increasing from -infinity to -3. Then it's decreasing from -3 to +3. And then it's increasing from 3 to infinity. And again, I'm reading it along the x-axis. Okay, now I need to clarify one thing. If you have more than one interval, so notice that we had 2 intervals of increase, should you use the union symbol in between the intervals? And the answer to that is no. Now why? In this case, we would not use that union symbol in between the intervals because if, remember, the union of 2 sets means that we're combining the 2 sets. So you're finding elements that are like in set A or set B. But if you, in this case, think of the union of these 2 sets, then the function would have to be increasing from -infinity to -3, increasing from 3 to infinity, but it would have to keep increasing. So, you know, yes, this part of the graph is increasing, you know, but this point is lower than this point. So let's say that you had something like, I'll try to make maybe a better example. Something like this. Then you could use that union symbol in between those intervals because, you know, the graph is increasing on this interval and then it continues to increase where it left off on the next interval because it's increasing, then constant, then increasing. So the union of those 2 sets would represent the idea that the function is increasing on the union of the sets, okay? I know that's a little confusing, so my best advice so that you don't have to think through all of that is just don't use the union symbol when you're identifying intervals of increase, decrease, or where the function is constant. So what do? You can put a comma in between. You can put a comma in between the intervals, or sometimes you'll see it just written as the word and instead of an or. Okay. All right, now, absolute extrema. And sometimes instead of the word absolute, we use the word global. Okay, so we're still talking about extreme values of the function, but when we're talking about absolute or global extrema, we are looking for like the highest point on the graph would be the absolute maximum, or the lowest point on the graph would be the absolute minimum. So we're not just identifying all the peaks and valleys throughout the graph. Like, we're really looking for some specific points when we're identifying our absolute extrema. Now here's like your definition. We say that f of x has an absolute or global maximum at x equals c if f of x is less than or equal to f of c for every x in the domain we are working on. Okay, so this is saying that these y values have to be less than or equal to this y value for all x, okay, in the interval we're working on, because it could be a case where the domain is not all real numbers. All right, we say that f of x has an absolute or global minimum at x equals c if f of x is greater than or equal to f of c. So again, we're saying all these y values are greater than or equal to this y value for every x in the domain we are working on. Okay, let's look at a graph, because it'll probably make more sense when you look at a graph. So let's say this is the graph of our function, and again, when you're finding the extrema of the function, you are looking for the high points and the low points, okay? So, you know, if we start with our relative, this is a relative max, this point is a relative min, this point is a relative max. Okay, so again, when you're finding relative extrema, you're just scanning across the graph and identifying the high points and the low points. Okay, to find the absolute extrema though, like when you're trying to find the absolute maximum, you're looking for the highest point on the graph. Okay, so this is a little bit more specific. So notice that this point right here would be the highest point on the graph. So this point could be classified as an absolute and a relative maximum. Okay, to find the absolute minimum, we're looking for the lowest point on the graph. So that would actually be this endpoint right here. That is the lowest point on this graph. So what's kind of interesting is absolute extrema can occur at an endpoint, but relative extrema do not occur at an endpoint, okay? Okay, and also, before we move on to concavity, I want to also say that it is possible for a graph to not have any absolute extrema. So, I mean, imagine this is our graph with arrows on the end, and it keeps going forever. There's no way you're going to be able to identify the highest point or the lowest point on that graph. Okay, so there is no absolute extrema for this function. But let's say maybe like your graph is a parabola. The vertex of the parabola we could identify as a relative and absolute minimum. But this graph would have no relative or absolute maxima, okay? If the parabola opened down instead of opening up, then the vertex would be considered a relative and absolute maximum. Okay, so anyway, just trying to highlight that there are many possibilities when you're reading or interpreting these graphs. Okay, one last thing we have to talk about, and that is concavity. So again, concavity is just another way to describe the shape of the graph. And concavity describes the way that a curve bends. So if the function is linear, we would not describe linear functions as having concavity or being concave up or concave down. All right, so this is really specific to those curves, graphs that are curved. Okay, now very simply, concave up means that the graph looks like a U. Or sometimes we'll say the graph looks like a smile. Now, a more formal definition is for any 2 points in a given interval that lie on a curve, if the segment that connects them is above the curve, then the curve is said to be concave up. So notice this blue segment here. If I picked 2 points on this graph and I connect them with a line segment, the line segment is above the curve or graph of the function. Okay, concave down is when the graph looks like a hill, or sometimes we'll say it looks like a frown. More formally, for any 2 points in a given interval that lie on a curve, if the segment that connects them is below the curve, then the curve is said to be concave down. So again, here's an example. If we picked 2 points on this graph and we connected those 2 points, notice that that line segment is below the curve. All right, now, it is possible that the graph of a function changes concavity. So the function might be concave up on one interval, but then change to concave down. The point where the curve changes concavity is called an inflection point, okay? So if you look at this first graph, and again, if we're writing intervals of concavity, we're reading the graph along the x-axis, all right? You know, so here's negative infinity, here's infinity. Notice that this graph looks like a hill until we get to this point right here, where it looks like a frown, and then it looks like a smile. So this point is our inflection point, and that's going to be where the graph changes concavity. So it looks like that the x-coordinate of that point is +3. So, and again, you can do the same thing that we did with intervals of increase and decrease. Draw that dashed vertical line. We're breaking this up into 2 separate intervals. So this particular graph is concave down from negative infinity to +3, and then it's concave up from 3 to infinity. And just like the intervals of increase and decrease, we're going to use parentheses with our intervals of concavity. Again, because at that inflection point, that's where the change is occurring. All right, and then one more graph. This one, it might be a little bit harder to see the concavity, but there actually is a change in concavity. This graph is concave down again. To start off, from negative infinity to 0, which is where our inflection point is, and then the graph is concave up from 0 to infinity. And then x equals 0 is our inflection point, because that's where the change happens. So I'm just going to put IP for inflection point. And then over here, our inflection point was at x equals 3. All right, you guys, so I know that that was probably a lot to take in. We'll definitely practice it in class, and I'm sure you'll feel more confident with all of this after some practice. But as always, thank you for watching, and have a good night.